Everybody, we made it finally out of our bonding unit. It's like the never ending unit on bonding. But now that you know all about how elements can combine to form different forms of compounds, now we get to look at how elements and compounds react with each other to change into new and different substances. And so this is really exciting. I feel like this is where chemistry really begins. We're going to get to do some fun demos. And after this, we get to get into the math involved in chemical reactions as well, which is always fun to get into that. So without further ado, we are going to take some notes on the first few pages of our new unit packet, pages 2, 3, and 4. I'm going to go through this just sort of at the pace that it takes me to talk about it, and certainly please pause wherever you need to in order to take your notes. So here we go. Introduction to reactions. Maybe. Maybe not. There we go. I guess I have to click, not scroll. All right, so we learned in the very first few weeks of school what signs of chemical reactions looked like. I did a bunch of demos for you guys where you saw formation of a gas. Anytime you see a formation of a gas in solution, you'll see bubbles. That's one way to know a gas is being formed. Other gases are formed sort of more obviously as things burn. Formation of a precipitate. Remember, a precipitate is where a solid falls out of solution. Something all of a sudden becomes insoluble. Color changes. That's where I did that magic picture that kept changing color from colorless to pink. After doing your at-home cabbage indicator lab, you now know that it's very easy to get things to change color just with changes in pH. So one of the ways that we can see color change is by using an indicator. Other reactions, the substances themselves just change colors. It's not the indicator changing color, but in fact, as some substances get formed or as they decompose, they might change color as well. Certainly smell. And lastly, evolution of heat and light. So when we see flame. So those are our 5 signs of chemical change. Now, we are going to start writing reactions in chemical equations. So this is where things are becoming new to you. Or maybe it's just a review from middle school. The things that we write on the left-hand side of these chemical equations are the reactants, or the substances that we are starting with. The things that are made in that reaction are the products. And the reactants turn into the products, obviously. So this is a generic equation. We're going to work a lot with generic equations like A's and B's. And then we're going to do actual chemical reactions using element symbols as well. So a generic reaction could be something like substance A and substance B turn into substances C and D. Now, unlike nuclear reactions, the elements that you start with are the elements that you end with in a chemical reaction. So if we are starting off with hydrogen and oxygen in our reactants, we are going to have hydrogen and oxygen in our products, but we might just have them in a different proportion or a different form, we should say. So like, for example, we start off with pure hydrogen gas and pure oxygen gas and make water, but water is going to be composed of that hydrogen and oxygen that we started with, obviously, because matter is conserved in chemical reactions. So there's no formation of like new atoms. You get formation of new substances because the elements combine or separate in different proportions, but you're not going to get new atoms of new elements like you get in a nuclear decay equation. So that's very different than what we learned about back in Unit 2. So A and B are our reactants, C and D are our products. An example of an actual reaction would be iron mixing with oxygen to make iron 3 oxide. That's rust. That's the reaction that produces the rust you see on your car or, your house. So again, get familiar with this generic sort of equation that we're going to work with. as well as what actual equations look like. Now, we can represent these reactions in 3 different ways. The first way is a sentence. So if you guys are ever reading a scientific paper, or you're reading about, maybe it's not even a scientific paper, maybe you're reading about something going on about COVID, and you're reading a newspaper article describing the chemical reaction that takes place in the body with some new drug, hopefully, you might read a sentence as opposed to a chemical equation. So here's a sentence that describes a reaction. Copper reacts with chlorine to form copper 2 chloride. So that's how it would sound. Now, for chemists, we don't need the whole sentence, right? Like we can use symbols because we know what those symbols mean. So we can take this, kind of clunky sentence that you might see in a paper and shorten it. And there's 2 ways to shorten it. The first way is a word also called a skeleton equation, where basically we just take out all of the extra words except for the substances. So we say copper, and then for reacts with, we use a plus sign. And for the to form, we use an arrow. And then there's your product, copper 2 chloride. So it's called a word or a skeleton equation. And then the most common is an actual chemical equation, where we take those words and those names of those elements and those compounds, and we write their formulas. Now, this is why it was so important that we learned how to write names and formulas of substances, because when we go to write reactions, we need to know that copper is an element and it's Cu. We need to know that chlorine is a diatomic element. So it's one of those 7 diatomics. Remember Brinkelhoff? So it needs to be Cl subscript 2. And we know how to write formulas for ionic compounds. This is a blast from the past. It seems like a long time ago that we were doing ionic. We have to balance our charges. So copper has a 2+ charge. That's what that Roman numeral there means. And chlorine has a 1- charge. So you need CuCl2 as the formula for the product. In fact, I think I'm actually going to switch over really quickly to my smooth draw here. Hopefully. There we go. And I want to write out for you what I was just saying in words. So Cu, this is copper, has a 2+ charge. Chlorine has a 1- charge. And so the formula for copper 2 chloride is CuCl2. It was a coincidence, like we did not just take the copper from the reaction and the chlorine from the reaction and just smush them together to make CuCl2. That, unfortunately, was a coincidence that I happened to choose something with a 2+ charge and a diatomic element. In other words, if I had said it was copper 1 chloride, right? So it's quite possible that this reaction takes place like this and makes not copper 2 chloride, but copper 1 chloride. The formula would be CuCl. Because if it's copper 1 chloride, copper with a 1+, chlorine with a 1- would make that formula of the product. So we're not just going to take these elements and smush them together to make the product. We're going to actually balance out the charges and figure out what the correct formula for the product is. And for those of you that are really thinking ahead, you might be looking at this and saying, wait a second, Ms. Rivera, there's 2 chlorines here on the left and only 1 here on the right. What about law of conservation of matter? And I would say, very good question. We're going to have to add coefficients to these equations where we put a 2 out in front here and we put a 2 out in front here to make sure that the numbers of atoms of copper and chlorine on the left match up to the numbers of copper and chlorine on the right. We'll save that for our next lecture. That's called balancing a chemical equation. I've gotten way off track, you guys. All we were looking at was a simple chemical equation, And I just wanted to make sure you guys understood why the formula for the product is what it is. Okay? It's not a smushing together of things. If the product is ionic, we got this product by balancing charge. That's all I wanted to do. That probably was way too long a tangent. But you know me, I love a tangent. All right, let's get back to our PowerPoint. All right. So in order to go from a sentence or a word equation, to go from a sentence to a word equation or to a full chemical equation, we need some symbols. And so these are the symbols that we use in order to write chemical equations. The arrow is the symbol that we use to show that the reaction is taking place. So it can be substituted in for words like produce, form, decompose, combusts, rusts. Like anytime you're hearing a word that sounds like the reaction is taking place, that's your separator between your reactants and your products. If you're using multiple reactants or you're producing multiple products, you're going to use a plus sign. We're going to use small letters in parentheses to indicate the state of matter of all of the substances involved in the reaction. So solids, liquids, gases, and things that are dissolved in water are aqueous. We put a triangle over the arrow for reactions that need heat in order to occur. Most reactions are actually reversible. We won't look at this year, but next year in AP, we'll learn about equilibrium and reversible reactions. If you see arrows going in both directions, that means that the reaction is reversible. And if you see an element symbol or a compound symbol over the arrow, that's indicating that a catalyst is being used. A catalyst is neither a reactant nor a product. It is simply something that makes the reaction happen more quickly. Think about like enzymes in biology. Enzymes are catalysts. They bond to the reactant molecules and help orient them in a way to make that reaction happen faster. All right, so if you need to pause there to write those symbols down, go ahead and do so. Let's talk a little bit more about these coefficients, symbols, and states of matter. So when we're looking at a chemical equation, it's telling us a whole bunch of information. It's telling us how many of each thing is involved in the reaction. And that is told to us by looking at this coefficient. So this coefficient out here means that this reaction is using 2 molecules of hydrogen and 1 molecule of oxygen. The ones are understood or omitted, in order to make 2 molecules of water. Okay, so if you want to know how many of each thing is required for the reaction to take place, it's like your recipe, you look at those coefficients. Now those coefficients are also going to represent something called moles, which we will talk about in our next unit. Of what is the substance, right? So this is telling me that I needed 2 molecules of what? Hydrogen gas. And 1 molecule of what? Oxygen gas. And 2 molecules of what? Dihydrogen monoxide, or water. And then finally, our states of matter. So you want to make sure if you have a good balanced chemical equation, it tells you all 3 of those key pieces of information. How many, of what, and in what state. So let's go ahead and see if we can take this sentence and turn it into a balanced chemical equation based on what we just learned. So this first part of the, I don't know why some of these are underlined and some of them aren't. I think what happened when I switched it from PowerPoint to Google Slides is some of my formatting got wonked up. Okay, sorry, that was irrelevant. 2 atoms of aluminum. Well, how am I going to indicate 2 atoms of aluminum? Oh, there's my underline. I'm going to put a coefficient of a 2 out in front. No, I didn't want to exit. I wanted that thing to go away. That's annoying that that's down there. I won't put my pointer down there or else it will appear. So in order to show 2 atoms of aluminum, I put my coefficient of my 2 out in front of the aluminum. Remember, aluminum is not one of our diatomic elements. It's not going to be Al subscript 2. And we also learned that the how many is a coefficient, right? The of what is the substance with whatever subscript that it has. So 2 atoms of aluminum. How did I know that aluminum was solid? Well, I looked on my periodic table and it's black, and black means solid. I also know that it's a metal, and all metals except for mercury are solids at room temperature. Next part of my sentence is the reacts with. That's going to be my plus sign. 3 units of aqueous copper 2 chloride. Oh, there's that copper 2 chloride again. The 3 units of it is going to be my coefficient. Copper 2 chloride, I balance my charges to write the formula CuCl2. And of course it's aqueous, so I'm going to use my AQ symbol. To produce, there's my arrow. 3 atoms of copper. So again, the 3 atoms, the coefficient, and copper is a solid. And 2 units of aqueous aluminum chloride. So the 2 is my coefficient. For aluminum chloride, I have to balance my charges. Aluminum has a 3+ charge. Chlorine has a 1-. So my formula is AlCl3. Now you might have noticed in this example that I used some different vocabulary. I didn't use the word molecules because nothing was covalent. On that previous slide where we were talking about the water and the hydrogen and the oxygen, I kept saying the word molecules because we use that word molecules for covalent substances. Here you see me use the word atoms and units. And that's because when we're talking about elements like aluminum, we would use the word atoms because we're not talking about a compound. And when we talk about ionic compounds like copper 2 chloride and aluminum chloride, we don't use the word molecules because they have a crystal lattice structure. And it wouldn't make sense to use the word atoms either because it's a compound. So we use the word units. So let's put that into our notes. These coefficients and the how many of each substance, we will use different vocabulary. Again, for elements, we're going to use atom. For ionic compounds, we're going to use unit. And for covalent compounds, we're going to use molecules. Now, for your 7 diatomic elements, because they are in fact molecules, we're going to use the word molecules. I know they are, a pure molecule composed of 2 atoms of the same element, but still we'll use that word molecule because they are 2 atoms bonded together. Why don't you go ahead and pause right here and see if you can assign the correct vocabulary for these 4 different substances. Did you do it? All right, this first one, carbon dioxide, is covalent. So this would be 3 molecules of carbon dioxide. Magnesium is an element, so 2 atoms of magnesium. Magnesium oxide is an ionic salt, so we would use the word units. There's that stupid thing again that keeps popping up. And lastly is our diatomic hydrogen, 2 molecules of hydrogen. Let's see if we can go in reverse. Let's see if we can take this chemical equation and turn it into a sentence. So I look at this first thing right here, and that is zinc. And zinc is an element, and there's 1 of them. So 1 atom of solid zinc. For this plus sign, it's going to react with. What is it reacting with? It is reacting with 2. Now, this is an acid, okay? Acids we often refer to, remember we said they kind of ride the line between ionic and covalent. They are like very, very polar covalent, and in water, they break apart into their ions. So for this acid, we're going to use the word molecules because it's a non-metal combination, kind of ionic, kind of covalent. We're going to go with the molecules of aqueous hydrochloric acid. It's one of your binary acids, so we use the word hydro in the front. To produce metal, non-metal, this is an ionic compound, so 1 unit of aqueous zinc chloride. Even though zinc is a transition metal, we're not going to put a Roman numeral in the name. Remember, zinc is always a 2+, and silver is always a 1+. Otherwise, your transition metals would have Roman numerals in their names. And 1 molecule of hydrogen gas. The good news, you guys, is we're not going to be going into sentences very often, but you do need to be able to read a sentence and turn it into an equation. We're going to be working with equations from now until the end of the course. So we have to be able to write formulas for different substances. Ooh, and that's it. That was my last example. Let me check the packet, make sure I covered everything that I wanted to cover for today. Excellent. Okay, so there is practice for you guys to do with this on page 5. At the top of page 5, you're going to be going from sentences into equations. And at the bottom of page 5, you're going to go from equations into sentences, which is a little bit harder. So just pay attention to how many of what, that's where you have to figure out the right formula of the substance, and in what state. And it doesn't matter if you put the state of matter before or after in your sentence. Like if you said aqueous hydrochloric acid, or you said hydrogen gas, you know, in one place I put the state of matter in front, and in the other place I put it at the back. It doesn't matter. You could have also said gaseous hydrogen. So it doesn't matter where you put the state of matter as long as it is in there. And then obviously the most important thing is that you have the correct formula for the substance. And if you are struggling with writing formulas for substances, Google it or come for some extra help. All right, you guys, I will see you at our next lecture on balancing equations.